Okay, folks, so let's look at a linear model now. It seems, I mean, we were looking at linear costs before, so it's almost stands to reason that investments, since they're based on money too, might be linear as well. So what we're going to do is we're going to take a look back to a really basic linear cost. So if you think back to, like, we were looking at LED light bulbs, CFLs, incandescents, hybrid cars versus pure gas cars, things like that. There was always an independent variable, and then there was a dependent variable that was some kind of a function on the independent variable. So I'm not going to get down in the mud of context in this video because I want to focus only on the math. So I'm going to make the independent variable just be 0, 1, 2, 3, 4. We'll go to 5, I guess. 5 plus I'm out of board, so 5 will work. The dependent variable, let's make it be, I know we looked at a lot of like fixed and variable costs, so let's just make this a really simple one because we're doing this on the board, on the fly. Let's make it be 3, a fixed cost of 3, 3 something, doesn't matter what it is, plus 2 times the independent variable. So this would be your variable cost, and this would be your fixed cost. But the important thing is, don't worry about that. We're gonna stick those numbers into that and have the dependent pop out. So 2 times 0 is 0 plus 3 is 3. So if the independent variable is 0, the dependent variable is 3. I'm just gonna go quickly down and do the last 5. 1 times 2 is 2 plus 3 is 5. Your job is to keep track of me and make sure I don't screw this up. 2 times 2 is 4 plus 3 is 7. 3 times 2 is 6 plus 3 is 9. 4 times 2 is 8 plus 3 is 11. And 5 times 2 is 10 plus 3 is 13. All right, take a quick check of that, make sure they're all in line. Look pretty good? Looks pretty good. Sometimes I start writing diagonally when I'm standing off to the side like this. Okay, now what I want to look at next is I want to look at the changes, the deltas, I call them deltas sometimes, of the independent variables and the dependent variables. So what I'm going to do also is I'm going to erase this rule. We don't need this rule anymore. We just needed that to make sure you saw where I was getting these numbers from. This is now a linear relationship. And here's why. If you look at the deltas, delta in science means change. So if you look at how these numbers are changing, 0 to 1 is up by 1. 1 to 2 is up by 1. 2 to 3 is up by 1. 3 to 4 is up by 1. And 4 to 5 is up by 1. Absolutely. So I chose that intentionally. Let's look at the deltas on the dependent variables as well. And I think I'll use red for this. What would the delta dependence look like? Well, let's see. 3 to 5 is up by 2. 5 to 7 is up by 2. 7 to 9 is up by 2. Seeing a pattern here, I hope. Up by 2. Up by 2. Now, I bet you most of you realized this was going to happen because the original formula was fixed cost plus 2 times the independent variable. That was the slope. And that's what you're actually seeing here. The slope is delta over delta. So it's 2 over 1. The slope between the point 0, 3 and 1, 5 is the change in y, which is 2 over the change in x, which is 1. 2 over 1 is 2. 5 to 7 is up 2. 1 to 2 is up 1. That's also 2 over 1. As a matter of fact, nobody even makes you only go by 1. If you want, you can jump spots in a linear relationship. You know why this is the case. Let's use maybe green, because green is light blue. So you can jump, instead of going by a delta of 1, you can jump straight from, say, 0 to 3 and go up by 3. Well, if you go up by 3, then if you look at the delta that jumps 3 here, from 3 all the way to 9, that's up by 6. But think about the ratio. 6 to 3 is the same as 2 to 1. We hammered this point home pretty good with grade and also with linear modeling. It doesn't matter how hyper-focused you are on a slope of a line, it's a constant slope. It's always a constant slope. No matter where you pick on that line, it's always going to be a constant slope. And that's kind of the function. That's what lines do. They're consistent. Let's see if this applies to our financial model. So what I'm going to do is I'm going to run back in the office and I'm going to recreate this table in Excel, show you what I did here, but in there, and then we'll take a look at the exponential model and see if it kind of behaves the same way. All right, meet you back in the office.